start. So there are two things I want to do today. I want to come back a little bit to the computation of the exponents because I was too quick yesterday and it's never a bad thing to tell everything twice. And in addition, it will allow me to just speak about one more exponent in a way which is maybe not completely convincing, but something that is a bit puzzling to me. And then I will switch to the particular study of SLE 6 and SLE 8/3. So I will speak about the locality and the restriction properties. So recall what I was talking about in the end of the lecture yesterday. I was considering radial SLE, SLE kappa, for some kappa bigger than 4. And I wanted to compute the probability that you hit the circle of radius epsilon around 0 without, so this is 0, this is the circle of radius epsilon. You start an SLE from 1, and you want to know if you reach this circle without disconnecting, say, -1. And -1 was a test point. So the initial question is whether you hit the circle of radius epsilon without disconnecting the whole boundary, but it's kind of the same to look at whether you disconnect -1 from 0. So you want to arrive like that, like this, and the reason was to compute arm exponents for spin systems or for percolation. So if this occurs, that's because you have one arm on your right, and okay, maybe let's make the picture more generic. This is what really happened. And you have one arm on the right and one arm on the left that force you to go to the disk before you make a circle here. So remember, the argument was then to say that if you look at the tip at time t, and you look at the image of the picture by gt, then what you see is that, so the curve is mapped somewhere, -1 is mapped somewhere. So this is gt of -1. This is e to the I beta t, which is gt of gamma t. And the image of the curve is something like this, and 0 is fixed, somewhere in the middle. Okay, and then I told you that one way to attack the problem was to look at the angle here between e to the I beta t and gt of -1, which I called theta t. So I'm repeating essentially what I did yesterday and probably what Hugo did in his TA session. So maybe repeating 3 times is a little bit too much, but I want to reach something. So if you look at theta t, it's the ratio of this by this, and the evolution of that is given by Ito's formula. And what you get is that d of theta t is, well, there's a Brownian term coming from here, which is square root of kappa dbt. And then there is a drift term coming from Loewen's equation, from the vector field in the equation. And this turns out to be, if you write it in polar coordinates like theta t, is cotangent of theta t over 2 dt. So it has a strong drift positive when it wants to reach 0, and it has a drift which is negative when it wants to reach 2 pi. So theta t is 0 and 2 pi. So I want to redo the picture I did yesterday about the arms and what you are allowed to do, because then I want to distinguish 3 cases in what happens. And that's one picture I did, but maybe I didn't spend enough time on it. So the really important thing is to understand what happens when you close a loop around 0. So I need a red here. So what happens if you close a loop like this? That's a trick that I learned from Wendelin. It's a very good trick. Okay, what happens just before you hit the boundary? So this is gamma times tau plus epsilon. This is 0, and there will be a map from this to the unit disk, like this. So it will map the two sides of the curve to two different intervals, and one will be yellow and one will be red. So maybe this is e to the I beta t. And I want to mark one particular point on the picture, which is this point here, which is the point at which you will close the loop. So if you want to look at the image of this interval on the boundary of the curve here, well, you can look at harmonic measure from 0, meaning that you can launch a planar Brownian motion from 0 and look at the probability that you hit the boundary here as opposed to anywhere else. So by conformally invariance, the length of the image of this curve here will exactly be 2 pi times the harmonic measure. So if the harmonic measure is very close to 1, the image will be very close to being the whole circle here. That means that the image of this part of the yellow here will start from gamma, will turn clockwise, and will be essentially the whole circle. So this will be the image of the yellow part of the curve. It will reach all the way here. And the image of the blue point will be somewhere here, which is also very close to the tip here. Okay, and then there's the image of the red part of the curve, and the red part of the curve is on the other side of the driving function, but it has to be very small because it has to be contained here. And then there's the image of -1. And -1 is in the white part of the boundary, so GT of -1 is somewhere here. And of course, as you shrink the opening of the loop here, everything that happens here will shrink to 0, and eventually GT of -1 will reach e to the I beta t. So maybe this picture is good to see a few times, because then you really understand what happens when you close a loop. Okay, and if you look at the direction in which things happen, here you will notice that the blue point, which is here, is on the left of e to the I beta t. So if you measure the angle, how do you measure the angle in this direction? Then you notice that theta goes to 0 in this case. So this is theta t going to 0. If you close the loop in the other direction, then the situation is reversed. The red and yellow are exchanged in the picture, and GT of -1 will approach from the other side, so that will mean that theta t goes to +infinity. And then at the moment that you close the loop, here, if you see this as exploration of percolation, you will notice that the moment you close the loop is exactly the moment where there is a yellow circuit around 0. So what it tells you is that theta t going to 0 implies that there is a yellow circuit. And if theta t goes to 2 pi, then there is a red circuit. So then if you want to have two arms, one red and one yellow, all the way to the disk here, it means that none of these circuits is allowed, so you need to avoid both 0 and 2 pi. If you want just a yellow arm, it means that it's allowed to have yellow circuits, but it's not allowed to have red circuits, so you can touch on one side of the interval and not on the other one. And the third case is where you are allowed to touch on both sides. So the natural question is what you do once you have touched. How can you continue here? And it turns out that the right way to do that is to take this reflection and this diffusion and to reflect it on the part of the boundary which is allowed to touch. Essentially, you restart infinitesimally close to your starting point here. That means that if theta was at 0, you restart just at 0 plus epsilon, and then you iterate every time you close a loop in this direction you just bounce on the boundary. Okay, so what it means is that if you want to look at the survival probability, you look at the generator and you want to find eigenfunctions for the generator. In other words, you are looking at the generator, which is kappa over 2 times the second derivative plus cotangent x over 2 times the first derivative. So this will be L kappa of f. So that will be kappa over 2 f double prime plus cotangent x over 2 x prime, f prime. The survival probability of a diffusion in an interval is given by the leading eigenvalue of the generator. And the leading eigenvalue of the generator is the one that corresponds to a positive eigenfunction. This is the same as the Perron-Frobenius theorem in the discrete case. So you want to look at a positive eigenfunction of L kappa. And you want to adapt the boundary conditions of the eigenfunction to the boundary conditions of the diffusion. So depending if you want to look at the 2-arm event or the 1-arm event or the 0-arm event somehow, then the boundary conditions will be different. So let me just list what you can do. If you want to look at the 2-arm event, it means that you kill the diffusion when you hit any of the boundary points. And it means that the boundary conditions are Dirichlet. And then it turns out that, well, you can find the positive eigenfunction. The positive eigenfunction is sine of x over 2 to the power 1 minus kappa over 4. So this is an eigenfunction and it's positive. And the eigenvalue corresponding to that is what I wrote as the 2-arm exponent, and this was equal to something like 1 minus 4 over kappa. That was, yeah. So the lambda was 1 minus 4 over kappa. Was it true? It's not true. It's not true at all. It's kappa minus 4 over 8. Okay, I just want to mention that, in fact, because this is such a simple generator, you can find the whole list of eigenvalues and you can find a whole list of eigenfunctions in terms of trigonometric polynomials. And there is a countable list of eigenvalues in this case, which are equal to, so lambda k is k plus 1 kappa minus 2 squared minus 4 over 8 kappa. Okay, so it goes to infinity, that's okay. And the leading eigenvalue is the one for which k is equal to 0. So it matches this when k is equal to 0, hopefully. So in particular for kappa equal to 6, you see that this is 1/4, and then the other eigenvalues tell you something. The other eigenvalues tell you essentially how quickly you converge in distribution to the SLE conditioned not to disconnect if you look at it in the neighborhood of 0. So if you condition not to disconnect, it means that you are projecting essentially on something related to the first eigenvalue, and then the other terms tell you how quickly you forget about the shape of the boundary if you look at the conditioned process. So for this case, it's not really interesting to look at this conditioning, but it will come back in the third case. So case number 2 is the case of the 1-arm exponent. So for the 1-arm exponent, you are allowed to touch on one side but not the other side. It means that the correct boundary condition is mixed, Dirichlet on one side and Neumann on the other one. So Dirichlet and Neumann, Dirichlet at 0 and Neumann at 2 pi, for instance. So you can do the same. The eigenfunction is sine x over 4 to the power, the same power. And then you find, again, a complete family of eigenvalues, which is 2k plus 1 times kappa squared minus 16 over 32 kappa. 32 kappa, yes. So this is a k, and the others are kappas. So again, you can essentially diagonalize everything, and you can find the whole family of eigenvalues. And again, this is for k positive. And again, the first one tells you the probability of the event that you don't close loops in one direction, but you are allowed to close in the other direction. And the other terms tell you how quickly you converge if you condition by this event. So it tells you something about something that looks like the incipient cluster for percolation. So this should be related to the IIC. But so far, it's not exactly explicit how it's related to the IIC. So I just want to mention the third case before I switch to the real content of this lecture today. So the last case, if you look at the natural boundary conditions, is Neumann on both sides. Well, then it's easy to find a positive eigenvector. You just take a constant, and the constant is an eigenfunction for this with eigenvalue 0, and it's perfectly good. So in this case, you seem like nothing is happening, but in fact, you can also diagonalize everything. So lambda k in this case is equal to k times kappa plus 2 squared minus 4 over 8 kappa. So of course, if you look at k equal to 0, you find 0. And it means that the leading eigenvalue tells you nothing. That's OK, because what you're doing is you're allowing the process to close loops in any direction. So you are not imposing anything on the curve. But the second eigenvalue tells you how quickly you converge to anything, so how quickly you forget about the shape of the boundary. And so lambda 1, what you get is something like kappa plus 2 squared minus 4 over 8 kappa. And if you compute that for kappa equal to 6, in the case of percolation, what you get is lambda 1 equals to 5 over 4. So what it tells you is that the way at which you forget about the shape of the boundary is driven by this eigenvalue, which is 5 over 4. And if you remember the course by Jeff and Christoph, you saw this exponent already. It was the exponent giving the 4-arm configuration probability, and it had to do with the correlation length. So that's one way of getting, for cheap, the 4-arm exponent without computing all the exponents. Saying that this is the rate at which you forget the boundary tells you essentially that this is related to the correlation length. And so you can argue that this has to be this exponent alpha 4 of percolation. OK, so that was for computations using SLE, and I will just stop here. But I just wanted to draw this picture again and maybe mention this 5 over 4. So that's not the canonical proof that alpha 4 is equal to 5 over 4. But maybe it tells something interesting about the model anyway. OK, so now I'll switch to what I wanted to really say today. So yesterday I mentioned that if you want to identify the value of kappa for a given discrete model, one good strategy was to compute the scaling limit of one probability in the discrete model, to compute the probability of the corresponding event on the continuous model using SLE, and then find kappa so that the probabilities match. And that's one way we identified that for percolation, the correct value of kappa was equal to 6. So today I want to do something a little bit more, let's say, more predictive. I want to predict what kappa should be for percolation without, well, before doing a computation of the probability of some event. So here I want to speak about the locality property. So what that means is the following. So I'll restart with the discrete model. So here's the upper half plane. It's discretized somehow by the triangular lattice at mesh delta. Delta will go to 0 eventually. And I'm looking at critical percolation, which I'm exploring from 0. So that's the usual picture. There are two boundary conditions here, and I start an exploration curve doing something like that. So this is gamma at scale delta. So this is perfectly well defined, but the remark is that it's always the same remark. If you want to explore percolation, you can do it by discovering the colors of the vertices along the path as you need them, and turn left if it's pink and turn right if it's orange. So this exploration curve here only depends on what you saw on the neighborhood of the curve. So only on essentially the outer boundary plus the boundaries of the loops inside. And what you read in the configuration is just a product measure. So you just toss independent coins as you go. So it depends on nothing outside of the curve. In particular, if you fix some compact set that touches the boundary, like this, so if you fix A, which is some compact set which is connected to touches the boundary, the complement is simply connected, and it is at positive distance from the origin, so the distance is positive. So such an A, I will call it a hull. If you fix such an A and you look at the exploration of percolation before you touch A, you just don't see that A is there. You will do the same choices. You will toss the same coin, whether you are exploring the percolation in H or in H minus A. So if you introduce big T, which is T sub A, which is the first heating time of A by the exploration curve, so it's a T which depends on the scale, then you expect, and you know on the discrete level, that gamma delta in H and the exploration in H minus A, they are exactly the same process. So they are the same up to time Ta delta. Meaning that the first time you notice that the domain is not H but H minus something is when you reach the boundary of the something that you have removed. And then, of course, once gamma touches here, so this is Ta delta, once you reach A, then the behavior will be different because the curve in H can enter A and the curve in H minus A will bounce on the boundary. So they have to differ after Ta, but up till Ta, they have the same distribution. So again, if you assume that there is a scaling limit for percolation and the scaling limit is conformally invariant, you would expect this to hold in the scaling limit. So this should hold in the limit as delta goes to 0. So if in addition you have conformal invariance, it tells you that to obtain the process in H minus A, you have two choices. You can look at the process in H and stop it when it touches A. Or you can look at the process in H minus A like I defined SLE in other domains, meaning you look at SLE in H and you map it back by the map that removes A. So that gives you two definitions for the continuous analogues of these two. And you predict that they should match at least for the kappa corresponding to the scaling limit of percolation. So this was some motivation for the locality property. So what I will tell you now is that this implies, in the case of SLE, it implies that kappa is equal to 6. So the theorem will be that there is exactly one SLE satisfying the locality property, and that's SLE for kappa equal to 6. So SLE 6 is really special in this way. It really grows locally without seeing the global picture, without seeing the shape of the domain. And as long as it doesn't touch a boundary, it doesn't see the boundary at all in distribution. So how do you prove such a result? Well, I already gave you the main idea. We will look at two possible definitions of SLE in the complement of A. So there is the initial SLE up to touching A, and there is the image of SLE by the map that adds A to the domain. So you have two processes, and these two processes are exactly growing curves in the upper half plane. So you can encode both using Leubniz's equation. And if you do that, you will get two driving processes, one for each version of the process. And by comparing the two, you will say that if locality is indeed satisfied by the process, the two driving functions should be the same. And then you will write that the difference is equal to 0, and this will give you an equation satisfied by kappa. And if you solve that, you will get that kappa is equal to 6. So that's more or less the strategy we want to apply. So here's the picture. We are still working in the upper half plane. So A is some obstacle in H. So this is the initial setup. This is the upper half plane, and I will use maybe yellow for the obstacle. Maybe a little bit bigger. So A is a hull here at positive distance from 0. 0 is somewhere here. And this curve here, for the moment, it's any SLE. So this is gamma t, and this is an SLE for some parameter kappa. And I'm drawing the picture for kappa smaller than 4 because it's just easier to draw. But eventually, you should think that kappa will be equal to 6. So this curve will bounce on the boundary many times. OK, so what do we have in terms of tools to attack the situation? Well, first of all, because we have an SLE, we have a conformal map GT, which removes this part of the curve, which maps the complement of this curve back to the upper half plane. So let me draw the upper half plane here. So GT maps this part of the curve to some interval in the boundary, maps the tip to beta t again, and it does something to A. It will map A somehow because it's opening the domain and shifting everything. So maybe it will map A to something like that. So this is GT of A. So this is the picture we want to understand. We want to understand how A is deformed and how the process is affected if instead of doing that, we look at the process in the complement of A. So as I said, if you want to define the process in the complement of A, there is one additional map that you might need, and that's the map that removes A. So here is the upper half plane again. And we are going to look at the map that removes A, which I want to call phi sub A. And phi sub A is normalized the same way as GT. So it's Z plus big O of 1 over Z plus other terms. So that's the map that removes A. So it sends the boundary of A somewhere here in yellow. It sends the origin somewhere. And from this somewhere, there is the image of gamma t. So this is the image of, so this is phi A of gamma t. Okay, so as I said before, if you want to define SLE in the complement of A, what you do is you take SLE here, starting from this point. So you shift this back to 0 and take an SLE. And then you pull it back by phi A, and it gives you SLE in the complement of A. Yes? The distance from A to 0 is assumed to be positive.
Oh, not to the x-axis.
Sorry?
The distance from A to the x-axis is not assumed.
Well, A is assumed to sit on top of the x-axis. So that's something I said, and I didn't write it, that the complement of A is assumed to be simply connected. So you don't change the topology by removing A. So this is the picture. Okay, so if SLE in the complement of A has to be SLE up to the heating time of A, it means that the way to obtain SLE is to start with SLE here and map it back by phi A. And this is equivalent to saying that the image of this curve by phi here should be the same as an SLE. So how to test that? Well, you have this curve in the upper half plane. You know that there is a conformal map, GT tilde, that removes this curve here. And so this is the final picture that you have. You have removed the curve, and you have removed the obstacle. There is no yellow anymore. Here. And you have removed the obstacle here. And so, well, there is a question of the time parameter, which I'm coming back to very soon. But this is a one-parameter family of conformal maps with always the same normalization at infinity. And if this is an SLE, then GT tilde should look exactly like the one-parameter family of conformal maps from SLE. So if you want to show the locality property, what you need to show is that essentially G tilde T has the same distribution as GT, at least until you touch the part of the boundary which is yellow here. So that's essentially because there will be a time change in the middle, but that's what you need to show. Okay, so there's one last side here which will be useful here. So let me call HT this map here. So phi A is the same as H0. And HT is the conformal map that removes GT of A from H. And all the maps here are normalized at infinity in the same way. So because there is uniqueness every time, then this map here can be written in two ways. You can apply GT and then HT, or you can apply H0 and then G tilde T. So what you get from this is that G tilde T composed with H0 is the same as HT composed with GT. In other words, the way you obtain G tilde is to start from GT, which you know, and then you conjugate it on the left by HT minus 1 and on the right by H0. So that's a link between GT and G tilde T. So what about the time parameter? As you know, if you want to encode a curve in terms of a Loevner equation, you need to fix the parameterization of this curve in such a way that the capacity here should grow linearly. So here you need to measure the capacity. So what you have is that, so the first thing you can look at is the capacity of the whole thing that you remove here, which means that it's the term in 1 over z in this map here. So this map will be z plus something like a of t over z plus other terms. So a of t is the capacity of this compact set, which is kt union A. But remember that if you compose two maps, two conformal maps that are normalized like this at infinity, the capacity is something that is additive. So you can compute A of t in two ways. It's the term in 1 over z of this composition, or the term in 1 over z in this composition. So if you first look at this, the term in 1 over z is 2t here. So this is equal to 2t plus the term in 1 over z for ht. And for ht, that's the capacity of gt of A. So that's A of gt of A. And this is not necessarily the same as the capacity of A itself, because it's deformed in a way that does not preserve the capacity. The map is not normalized by fixing the capacity of this guy, but by having a derivative at infinity, which encodes the capacity of the other one. And if you look at it the other way, well, here there will be the capacity of A plus this term here, which is the capacity of phi A of gamma t. So capacity of A plus capacity of phi A of kt. So this is what you have as a time parameter, but the relevant parameter is the capacity of this guy here, because that's the first thing you want to do if you want to normalize time to identify gt tilde. So the relevant one is this one here. That's really the one you would like to know. And what you will have is that dt, and I will tell you just right now why you need to look at the derivative, but dt of the capacity you really need to know, which is phi A of kt, this is the same as A prime of t. A prime of t being the derivative of the capacity of what you had to start with here. That's just because A of A is constant in this equation. Okay. So this is the picture, and now we want to say something about the family of maps gt tilde. So the topology is something that we have seen before. There is a curve growing into the upper half plane, and we have a family of conformal maps which is encoding the way that the curve grows, and it's encoding it by mapping the complement of the curve back to h. And these maps are normalized by the expansion at infinity. So this is almost the same as the framework in which I introduced Loevner's equation in the half plane. The only thing that you don't have is that the capacity is not equal to 2t here, it's equal to this A of phi A of kt. So what you will get is very similar to what you had before. The family of gt tilde will satisfy some differential equation, which will look very much like Loevner's equation. The only difference being that instead of having a term 2 on top of the gt of z minus beta t, what you have is the speed at which the curve is growing. So I could have used this from the start as a definition of a Loevner chain, but the 2 is a little bit more classical somehow, so I used the classical one. That's getting a bit dry. Okay, so what you have from the same proof as the proof of Loevner's equation, what you get is that gt tilde in the picture satisfies some differential equation which is related to the one you know already. So what you get is that the time derivative of gt is nothing but 1 over gt minus some driving function times A prime instead of times 2. So just a notation which is missing. This I want to call beta t tilde. That's just gt tilde of the tip here, and that's just ht of beta t. So you get something that looks like Lovener's equation. What you get is that dt of gt tilde of z is a prime of t divided by gt tilde of z minus beta tilde t. So this is Lovener's equation when the parameterization of the curve is not 2t. It's just a modification where there is a prime here. Okay, so if you want to know that gt tilde is the same in distribution up to time parameterization as SLE, well, this is equivalent to proving that beta tilde t is the same as Brownian motion with parameter square root of kappa in front and read in some time which is encoded by a prime of t. So in time a of t. I'm not writing a formula because last time I wrote a formula using Brownian motion. Apparently it was not completely exact. But this is what you need to show. You need to identify the driving function. And you need to prove that once you have done the time change to move back to the initial equation, what you get here is exactly the Brownian motion times square root of 6 in the case of kappa equal to 6. Okay, so how do you do that? Well, first of all, there is one thing that you will want to do. You want to look at what happens for a very small time because that's what this a prime of t tells you. So what happens if you add a little bit to the curve? I need the color. Blue is good. So you add something like this. So this is gamma at time t plus delta t, t plus epsilon. So this is mapped to all the steps in the picture. So it's mapped somewhere here. It's mapped somewhere here. And it's mapped somewhere here. Okay? So what you have is what? That the way in which the capacity here increases is the way in which the capacity of G tilde increases. So that's given by this A prime of t times epsilon. But on the other hand, if you look at what happens here, A has not played any role yet. So you know that the capacity of the blue thing here is equal to epsilon. So here the A of this thing is equal to epsilon, or to 2 epsilon. Okay? So then if you map it by ht, well, if you look at ht, it's a conformal map from the complement of gt of A to the upper half plane. But around beta t, the boundary is flat. So you know that ht, which is a holomorphic function, can be continued across a flat boundary by letting ht of z bar to be ht of z bar. And it tells you that h has to be smooth away from the boundary of the yellow thing. So in particular, around beta t, ht is smooth. And it behaves like a scaling. It has a derivative at beta t. And so this blue thing is really the image of this blue thing by a scaling of factor h prime of t. And then scaling changes the capacity according to Brownian scaling. So what you have is that the capacity of this thing here, this is equal to the capacity of this guy, which is 2 epsilon, times the square of the derivative of h at beta t. So times ht prime of beta t squared. Okay? On the other hand, this is the same as a prime of t times epsilon by this side here. So what you get is that a prime of t is equal to h prime t of beta t squared times, so there will be a 2 missing at some point. Okay, let me just fix this a little bit. So I will call a, well, the expansion will always be z plus 2a over z plus something. Just because it's simpler like that, you don't have all these 2's in the picture. And what you get is this. 2 here. And what you get is that a prime of t is equal to ht prime of beta t squared. So you can check that. So here again, there's a 2. You can check that if a is empty, h does nothing, and you get that a prime is 1, so a is linear, and you get the usual time parameterization of SLE. And as soon as you add something, as soon as you remove something from the domain, well, h does something, and the time parameterization is affected. So this tells you how the time parameter here lives. And it tells you that this numerator here can be read in terms of the map ht. Okay, so that was step 1. If you want to identify a curve using Loeffler's equation, the first thing to do is to identify the time parameter. And this is done. Now we need to identify the driving function. So what do we know? We know a few things. But mainly what we know is still that this function ht is smooth around beta t. So what we know is that we will be able somehow to apply Ito's formula. Beta tilde is the image of beta by h. So if we know beta t, which we do because it's square root of kappa times run in motion, and if we know h and its derivatives, then we can compute beta t tilde and write the generator of this guy. So what we need to know is something about ht around beta t. So remember, we have this commutation here. We can write ht from things that we know a little bit better. So ht is just gt tilde composed with h0 composed with gt. So what we will need is information about the derivatives of ht around beta t. So what do we have? At some point, well, there is a gt minus 1, of course, here. So if you look at ht of beta t and you want to look at how this behaves as a function of time, well, you will have a term in Ito's formula coming from the evolution of beta t, so that will be written in terms of space derivative of ht. And there will also be a time in time derivative of ht, because that's a composition relation. So the first thing you want to know is how ht evolves in time. And for that, you need to know how gt tilde evolves in time, and this you know. h0 is fixed, and you need to know how gt minus 1 evolves in time. And for that, so you just write that gt composed with gt minus 1 is constant. You know how gt evolves in time. And if you do that, well, what you find is that the way gt minus 1 evolves in time, so the time derivative of gt minus 1 of z, well, what I will write is not so surprising. Remember that the way we proved that gt was 1-to-1 was to show that there was a backwards flow of the same equation that gave you the inverse of gt. So you expect somehow that this should look like Loeffler's equation in backward time. So you expect something like minus 2 over a difference between something like this and something like this. So that's what you get if you do the computation. You get minus 2 over z minus beta t. But there is a term in gt minus 1 prime of z coming from the chain rule. So this is the time derivative of gt minus 1. And that's an easy computation. So I'm not giving you all the steps. I'm just telling you what you will get if you do the computations yourself. Okay, so this is the time derivative of this guy. We know the time derivative of this guy, gt tilde. And so if you do the computation using the chain rule, what you get is that dt ht of z. So it will be the sum of two terms, one from here and one from here. And so what you get is that, so the term on the left tells you that it's equal to this, but remember a prime is given by ht squared. So what you get is 2ht prime of beta t squared over ht of z minus beta t. So that's what you get when you differentiate with respect to this parameter here. And then minus something like 2ht prime of z over z minus beta t, which is coming from this equation here. But then you have to compose on the left, so what you get is ht prime here. Okay, so this is the time derivative of ht. And now we can look at what happens to beta tilde. So if you look at the evolution of beta tilde, well, the derivative of beta tilde in time, so d beta t tilde, what is it? Well, there is the time derivative of h. So what you will have is dtht applied at beta t dt plus whatever comes from the Ito formula. So that's something like dx of h. So ht prime of beta t d beta t plus ht double prime over 2 at beta t times dt times kappa. So that's what you get from Ito's formula and this relation here. Okay, we know almost everything. We have h prime and h double prime which occur all the time. What we want to know is what dt of ht is at point beta t. So we need to let z go to beta t here. So you take this, you let z go to beta t. And it turns out that this goes to 0, this goes to 0. But if you do an expansion, you'll notice that what do you need to do? That there's a problem in this. This is a tilde. As z goes to beta t, h of z goes to h of beta t, which is beta tilde t. And so these two go to 0 at the same time, but this is equal to this times h prime. So you notice that there will be some cancellation in the first order between the two terms. And what remains is something of second order. So what you get, if you do the computation, is that dtht of beta t turns out to be equal to minus ht double prime of beta t. So this is just computation. I apologize for doing computations like this, but it's not something fundamentally difficult. You just need to keep in mind where you are going, and eventually you get there. So we know now all the terms in this equation. The time derivative here is here. The space derivative at beta t will be natural because it's essentially the square root of a prime, so it's good. And the second derivative in space of ht, that's something that we really don't control. We don't really know what happens if you do if you look at the second derivative. But nevertheless, once you do that, what you get is that d beta t tilde has only one term which is Brownian, which is given by ht prime of beta t. So ht prime of beta t d beta t. Yes. And then there's a drift term coming from this and this. And what you do is what you can do is collect, and you notice that it is only written in terms of h double prime. So the h double prime, there will be something like -1 here plus kappa over 2 here. And if you are not wrong in the computation, what you get is kappa minus 6 over 2 ht double prime of beta t dt. So this is the driving function of the new copy of SLE. So let me recap what we did. We started from an SLE here, and we mapped it by the map that removes A. So we got this curve here, and we want to compare this curve with an SLE. So we compute the parameter, which is A, and we compute the driving function, which is beta tilde. And what we end up with is that the driving function A prime of t is this, and the driving function is given by this. So if you wish, this term here, ht prime of beta t, that's the square root of A prime. So if you do a time change, so you look at the process in the natural time of the curve, meaning that you look at it in time A instead of looking at it in time t. What you do is a time change with a coefficient which is ht prime squared. And so this will cancel, sorry, it's the square root of A prime, yes? So you do this time change. The Brownian scaling will tell you that this will cancel out exactly because of the square root here. And what you obtain is that in the new time, d beta hat s is exactly in distribution, d beta s plus kappa minus 6 over 2 times ht double prime of beta t over ht prime of beta t squared ds. That's an s. That's an okay, something. It's a t, but s is a function of t. So it's something like that. Okay, so what you know is that if kappa is equal to 6, then something magical occurs, that the drift term is equal to 0. So the drift vanishes. And what you get is that beta hat, so the new driving function in the natural time parameter of the curve, is the same in distribution as the initial driving function. So that's what you get. If kappa is equal to 6, and you take this image here and you look at it in the natural time parameter, then the driving function is the same as the driving function of this one, which is saying exactly that the image on the right here is exactly SLE. So this is equal to SLE6. So this is what we wanted. If you look here, you have SLE6 until you touch A, and you have the backward image of SLE6 by this map, which is SLE6 in the complement of A. And these are equal because they have the same driving process on the right. So this is what you get. So for kappa equal to 6, what you have is SLE6 in H up to the heating time of A, and SLE6 in H minus A, up to the heating time of A again, so that means heating time of the boundary, which is part of the boundary of A. So SLE6 also up to tau in tau sub A. So these two are identical. They have the same distribution. So this is known as the locality property for SLE6. And it's exactly what I told you in the beginning, that as long as you grow away from the obstacle A, then you don't know if you are growing in H or if you are growing in H minus A. And you only figure it out when you touch the boundary. Okay, so this is called the locality of SLE6. So it has a few very nice consequences. The first of all, the first consequence is that, okay, there's a converse to this theorem. If you take an SLE which has locality, it has to be SLE6, because this also proves to you that SLE for kappa different from 6 does not have the locality property, because this is not equal to 0. There is this kappa minus 6 in front, and H double prime cannot be equal to 0 here. Well, it cannot be equal to 0 all the time, because that would say that H prime is linear, and that would say that you remove nothing. So what you get here is that if percolation has a scaling limit, which is an SLE, it has to be SLE for kappa equal to 6. So corollary 1, if percolation converges as delta goes to 0 to an SLE kappa, then necessarily kappa is equal to 6. So this is a more natural proof that 6 is related to percolation. We don't have to fix one event and compute the probability and match the result. We start with one feature of the model. So the locality is one feature of percolation. And it has to be preserved in the scaling limit, so it gives you an identification of kappa, which is more, as I said, more predictive. You don't compute a lot, you just predict that it has to be kappa equal to 6. Okay, there's a second corollary, which is something about SLE6, which is not true, but it's not very wrong in the general case. So what you can do is the following. Assume you want to define SLE6 in some domain which is a subdomain of H. Assume you want to define SLE6 in a half disk from 0. Then you have a few choices. You can say, okay, the half disk is a simply connected domain, so I know how to define SLE6 in a simply connected domain from 0 to any boundary point. So I choose a boundary point, and I run SLE towards this boundary point. Okay, that's very good, but you need to choose a boundary point. Something else you can do is you take SLE6 in the upper half plane, and you intersect it with the half disk here, and it will look like an SLE, so you might want to say that it has to be somehow SLE in the half disk. But the problem is it doesn't really make sense to take information outside of the domain in which you want to define the model, because the model should be defined in a self-contained way inside the half disk. And so essentially, in this geometry, you have two choices. You can put the target point here, or you put the target point here. And you would like to say that, in fact, you don't want to choose. So here is one trick that you can apply. instead of looking at the whole half circle here, you can stop here. So you look at the circle between angle 0 and angle 2 pi minus epsilon. And then you look at SLE6 from 0 in the upper half plane. And you use this as the obstacle A that was the obstacle before. So you have two versions of the process. There is SLE in H until you touch A, and there is SLE in the complement of A towards infinity. Okay, and what you know is that these processes match up to the first time when you touch A. But because this is very small, you are very likely to touch the inside of the boundary here before you are able to escape through this opening. And so this picture here, up to time tau, is the same whether you are aiming at infinity or whether you are aiming at, well, whether you are aiming at infinity in the complement of A, or whether you are just living in the upper half plane but stopping when you hit the circle. Okay? And then as epsilon goes to 0, well, these two different processes each have a limit. One is, so SLE6 in H up to the time at which you hit the unit circle, which is the limit of SLE in H up to the time you hit A. And because the curve is continuous, as epsilon goes to 0, you cannot escape without touching the circle. So it converges to this. The other one is SLE in the complement of this part of a circle. And so this is SLE aiming somewhere which is on the other side of this fjord opening. So as epsilon goes to 0, whatever is outside is very small seen from 0. And so it turns out that as epsilon shrinks, this will converge to SLE in the half disk, aiming at whatever remains from infinity, which is this point here. When the opening closes, all the complement is shrunk at this point. And this tells you that this is equal to SLE6 in the half disk in this domain from 0 to -1, but also up to the first time when you hit the circle, because the locality tells you nothing about what happens after you hit the circle. So up to hitting S1. So these are the same processes. But you can notice that this one depends on the choice of a point on the boundary, which is -1. But this one does not depend on the choice of a point. There is no choice here. It's just SLE in H. So you can do it backwards, and it's the same as SLE6 in this domain from 0 to 0.1 this time, up to the hitting time of the circle. So you can just choose one by saying that instead of taking this arc, you start from 0 and you move all the way to this distance. Okay, so what it tells you is that essentially, well, not only SLE6 does not see in which domain it's living, but it doesn't see either where it's aiming for. So it doesn't know where the point at infinity is. And that's kind of natural because it really doesn't know if infinity is part of the domain because it doesn't see the shape of the domain. So what it tells you is that it is so local that it really only depends on the local geometry of the domain. And it can only figure out something about the global topology of the domain when it has to. So if you want a restatement of the last equality in distribution in a little bit more general way, so that really tells you something about SLE6 in a domain with 3 marked points on the boundary. So fix omega, which is a simply connected domain with a smooth boundary, and fix 3 points on the boundary of omega. So here's the picture. Omega is like this. This is A, and this is B1, and this is B2. And this is a part of the arc between B1 and B2. So if you restate this theorem over there, but instead of the half disk, you use conformal invariance to map the half disk to this domain, mapping 0 to A, mapping 1 to B1, and minus 1 to B2, what it tells you is that up to the first heating time, of the arc B1, B2 on the boundary, then SLE6 from A to B1, from A to B1 in omega, and SLE6 from A to B2 in omega. These are the same processes. So they are equal in distribution. So what it means is that if you want to define SLE6 in this domain, well, what you do is first you don't choose if you are going towards B1 and B2 or B2. So you just do your SLE. Sometimes you touch on this part of the boundary, and then it's still possible to go to either of them. And the only time at which you need to figure out if you are going to B1 or B2 is when you touch the boundary between them, because then it's just not possible to go from, if you look at SLE going to B1, it cannot enter here because this is swallowed by the curve, and you have to go towards B1 and you cannot cross your path. So if you go left, then you are trapped, and this is not what SLE does. So when you disconnect B1 from B2, what you have to do is choose. So the SLE to B1 will go here, and the SLE to B2 will go here. But that's the only difference between the two versions. If you are going towards B1 or if you are going towards B2, you do the same as long as you don't need to choose. So what it tells you is that essentially you can explore the whole percolation picture in the domain by saying, okay, maybe this will be a bit quick, but I'm pressed for time. So assume you want to say more than what I told you about percolation. What I told you about percolation is that if you put boundary conditions in a domain which are red on one side and white on the other side, and you look at the exploration curve, then this converges to SLE6. I told you this, and I more or less argued why this was true. And it was true because you had convergence of the crossing probabilities plus some tension coming from Russell-Seymour-Welles theory, essentially. So this gives you the following. If you take percolation in one domain, in a domain like this, and if you put two boundary conditions, like this and like this, then there is one natural interface, and this interface converges to SLE6. So this converges to SLE6. Well, of course, this is not the whole information about percolation, because SLE6 does not enter the loops, and the exploration is defined locally. So if you have a loop, you don't know what is inside the loop. So you would like to say something about more of the percolation picture than just one interface. So what you may want to do is, whenever you close a loop, well, the actual exploration picture continues outside because it's aiming at this point. But maybe you want to explore inside the loop. And maybe you want to discover the set of interfaces that are inside this cluster that you have just surrounded here. So you may want to construct some kind of branching SLE6 picture. And for any kappa, it's not clear how to do because the way in which SLE grows depends on the target point. But in the case of SLE6, the target point does not matter. So if you want to explore what's inside the bubble here, all you need to do is to pick arbitrarily a target point inside the bubble, presumably away from the point at which you close, and then you do an SLE6 towards this point inside the bubble. So it will tell you something like this. It will split the bubble into sub-bubbles like this, and every time you close one, you can branch and explore inside the bubble. And this property of SLE6 tells you that this is well defined, that what you get in the limit does not depend on which point on the boundary you choose, because the exploration processes, they match as long as they don't have to choose. So this is one possible approach to the full scaling limit. Of percolation. And this resplitting of the bubbles is more or less what Kamiya and Newman did in the paper on the full scaling limit. Okay, I think it's 12:30, so I'm not sure what to do. I have 15 minutes more, so I can start speaking about the restriction property. Or you can tell me that you are very hungry and we can go for lunch. I will just tell you about the restriction property without the computation, and I will do the computations tomorrow. So maybe not 15 minutes, but at least something non-zero. Okay, so where are we? We know that if you start with a discrete model, and it has a scaling limit and it's conformally invariant, blah, 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 then it has to be described by an SLE. And the task we have today is to find ways to identify the parameter kappa of the scaling limit. So if you can compute, you can match kappa. That's what we did yesterday. If you cannot compute, then what you need to do is find a feature of the discrete model that has a meaning in the scaling limit, and that is enough to identify the value of kappa. So in the case of percolation, the natural one was the locality property. Now I want to switch to a different model, one which is much more frustrating somehow because we don't know anything about it, or we know very little about it. And I mentioned it the first day, and that's the self-avoiding walk. So here is what you want to do. You want to define the uniform measure on self-avoiding path of a given length, and you are interested in the scaling limit of this. So if you want to say something about the scaling limit of this, you want to rescale the picture and somehow adjust the scaling to the number of steps in such a way that the scaling limit is not degenerate. But we don't know what the diameter of a self-avoiding walk is. We expect it to be some power of n, of the number of steps. But really, this power will be an outcome of the construction, so we cannot assume that we know it already. So one trick will be the same as for percolation. In the case of percolation, there was one way to produce an infinite interface from something which had only finite components, and that was building something in the upper half plane and forcing it to be infinite. So what you can do is this. So this is H. This is Z2 in H. And I will define omega n to be the set of self-avoiding walks in H intersection with Z2, which is Z times Z plus, from 0 with n steps. So it's just a set of paths that are attached at 0, and they have n steps inside the upper half plane. Maybe something like this. And what we want to know is the behavior of so mu n, which is the uniform measure on omega n. Okay, and as I told you, we don't know much about this set omega n. Essentially, all we know is that the cardinality of omega n behaves like some constant, which I want to call 1 over xc to the power n. So it's exponentially large. There will be a correction term which is polynomial in front, which is some universal exponent, but we don't know it, and we would like to compute it maybe using SLE. So in particular, we don't know the diameter of a typical element here. We want to construct something which is infinite, and it turns out, and this was done by Kesten, that what you can do is look at the first k steps of a walk of length n. So I look at mu n k, which is the law of the first k steps under mu n. So I take a walk uniformly of length n, and I look at the first k steps. So this is omega n, and this was omega k. And as it turns out, this converges as n goes to infinity to some measure nu k, which is a measure on omega k. It's a measure on walks of k steps. And it turns out that this measure is not uniform. It's not uniform because any of the walks in the support of nu k has to be continuable to infinity, because it comes from a limit as n goes to infinity. So there are walks that have no measure under nu k and had positive measure under mu k. Typically, this walk here, if you do this like that with 12 steps, then this has no measure under nu k because you cannot continue it, but it has measure 1 over cardinality of omega n under mu n. So this has no measure under nu k. So this is not uniform, but these measures mu k, nu k now are compatible. If you look at the measure of the first k minus 1 steps under nu k, well, it's easy to see that this is the same as nu k minus 1. So this is a family of compatible random distributions. And so you can extend it to a measure on infinite paths. So by Kolmogorov, what you get is that there is some new infinity on omega infinity, which is a set of infinite self-avoiding walks in the upper half plane, such that the restriction to the first k steps is nu k for all k. So that's the definition of the infinite self-avoiding walk. And it's not a uniform measure. It's just something that you should think of as essentially the natural definition of the infinite, of the uniform measure on omega infinity. But of course, this does not exist. So it's, well, it's this. It's the natural definition of a self-avoiding walk condition to be very long. Okay. So somehow if you talk to physicists, you expect some conformal invariance of nu infinity, in the sense that, so one more thing you can do is, so you look at nu infinity, that's a measure on discrete paths. What you do is then you take a scaling limit, you let the mesh of the lattice go to 0. So in the scaling limit. So you let the mesh of the lattice go to 0, and you get some random distribution, presumably in the limit, some random distribution on continuous curves in the upper half plane. So let's say that will be nu omega tilde which is some distribution on continuous curves in H, which are the same kind of the curves that we know how to study using SLE, using Leibniz equation. So you want to know something about that, and if you talk to physicists, they will tell you that this is conformally invariant. So you expect it to be one of the SLEs. So it should be SLE kappa for some kappa. And the question is which kappa? And then the first strategy we had was to compute something and to match it with an SLE computation. So if you can do this for the self-avoiding walk, you will be very famous because you cannot compute anything on the self-avoiding walk. So all we can do is to apply the second strategy, find a feature of the self-avoiding walk which makes sense for SLE, but which is specific to one value of kappa. And this is how we come to the restriction property. So let's do the same thing as before. Take an obstacle here and look at the measure which is self-avoiding walk in H. So I'm cheating here because there is an interversion of limits between this and what I'm writing, but I'm looking directly at the infinite self-avoiding walk. The self-avoiding walk in H conditioned to avoid the obstacle A. If you think of it in the finite setup, you are taking a uniform measure and you are conditioning it by an event. What you get by that is some probability measure supported by whatever remains outside of this event, or inside this event on which you are conditioning. But the probability of each possible outcome is still the same. You are conditioning a uniform measure, so it remains uniform. So you expect that self-avoiding walk in H conditioned to avoid A is the same as self-avoiding walk in H minus A. That's true and that's trivial if you are looking at a finite graph. And you expect it to hold for nu infinity, and you expect it to hold for the scaling limit. And so this should be the same as phi A minus 1 of the scaling limit. So it should be the same as phi A minus 1 of the self-avoiding walk in H. So here I'm using SAW to mean either the self-avoiding walk or the scaling limit. I'm just motivating what I'm going to talk about tomorrow. So in other words, if the self-avoiding walk has a scaling limit, you expect the scaling limit to satisfy this equality in distribution. If you condition the scaling limit to avoid A, then you should see the same thing as if you constructed the scaling limit in the complement of A in the first place. So this is what is known as the restriction property. And it turns out that what I will tell you tomorrow is that there is exactly one SLE for which this restriction property holds, and it's SLE for kappa equals to 8/3. So somehow this implies that kappa is equal to 8/3. So the plan tomorrow is to look at it from the SLE side and get to the conjecture that to the conjecture that self-avoiding walk actually converges to SLE itself. Well, of course, we don't know how to prove that, so that's just a conjecture at this point. Okay, so that's the plan for tomorrow, and now I think it's time to go for lunch. So, see you tomorrow. Unless there are questions.